don't know. Yeah, no.
Gosh, see, I thought we were.
I asked for information and it wasn't provided, so.
Okay.
I mean, they're getting the thing wrapped, it's gonna cost $3,000 to $5,000, so if there comes to work, we'll just not do that. But it's Toyota who funds that research. And this budget. That's why I wanted to get $1 million.
Anytime we ask him to come over, we can see him. Actually, I saw them dressed up yesterday. There's like 5. Yeah,
like a school bus. Like a school bus. Take out every other seat and put a table there. And you should put it on the road.
Yeah, I don't know that.
Yeah, but he's like in the driver's seat or something for the seat. Word on the back.
Yeah, we had much. I like it. Pretty aggressive.
Okay, so I want to finish up chapter 6 this week. So we will review on a week from today on Monday, and then our last exam in here will be on Wednesday before Thanksgiving break. And there is no final in this class. And since they moved the finals online, I'm not doing that. So the last 2 topics in the chapter, so we've talked a little bit about filtering and kind of gave you an introduction to filtering and design of Butterworth filters. The last 2 topics are modulation. So we'll kind of cover AM radio, how that works, amplitude modulation. It's pretty simple, but it's certainly an important application of the Fourier transform. Really, all that you need to understand modulation is the Fourier transform technique that we covered in the previous chapter. And then the last topic is on sampling, converting an analog signal into a digital signal. And that, again, that's kind of, it's the present as well as the future. It's been most media that we listen to now is converted into a digital signal. That's not true for AM radio and FM radio, but almost all other forms of communication are now digital. Your MP3 files, that's a digital file format. Your streaming audio and video formats are digital. Satellite radio is digital. You guys may remember it's been a few years ago since they made the switch from conventional television to HD TV. I forget when that happened, 2010 maybe. So you guys were fairly young, but may still remember having the older television sets that to receive conventional television. That was an analog signal. And I expect at some point, AM and FM radio will go away as well or be converted to a digital format. There's a lot of reasons for doing that. Now, that doesn't mean, a lot of people take that to mean, well, what is analog circuits going away? And the answer to that is no. Actually, with wireless communication, radio frequency communication, that's still that's still requires analog circuitry. We'll see that today. I mean, modulation of analog versus modulation of digital. About the only thing is what's the low frequency signal look like? Is it a digital waveform or is it an analog waveform, coming off of a microphone or coming out of a computer? The modulation circuitry, and we'll see this a little bit today, is still analog circuitry, that high frequency circuitry. So modulation, why do we modulate? Well, when we can't efficiently transmit a low frequency signal wirelessly, the antenna length has to be on the same order of magnitude as the wavelength. So, in audio frequencies, with the speed of light, the corresponding wavelength is hundreds of meters or more. And so, and you don't want to drive around with a 100-meter antenna on your car. There's a lot of places you can't go, a lot of bridges you can't cross under. So we have to translate up into the megahertz range where the antennas are on the order of a meter. Okay. So that's one reason for efficient radiation, wireless radiation. The other reason is important, even when you're not transmitting wirelessly, is that modulation allows you to do what's known as frequency domain multiplexing. That's a fancy way of saying it permits you to have channels that transmit different signals at different frequencies, different carrier frequencies, over the same medium. So, on your coax, on cable television, there are actually hundreds of different signals that come in over that coaxial cable, and then your cable box or your television selects the particular channel that you want to watch. I mean, they're all present there at the same time. And the same is true for wireless transmission. We have all of the different local radio and television stations transmitting different frequencies. So all of the signals are out there in the airwaves. We tune to the particular station we want to listen to, or the particular station we want to watch. And the reason it works is, one is that they use different carrier frequencies so that the signals are separated by frequency. And we'll see kind of how that works today. And then the other reason is, fortunately or unfortunately, depending on how you look at it, radio strength and television strength, the strength of the signal falls off the farther you are from the antenna. Okay, so that means you can only pick up your transmission in a certain geographical area. And that's probably a good thing, because that means, if we're transmitting a radio station at 1200 kilohertz here, there's another 1200 kilohertz station in St. Louis, and they won't interfere because they're just too far apart. So with modulation, we take a special signal that's called the carrier, and it's just a sinusoidal signal, okay, with an amplitude, a frequency, phase angle. So, and here it's called the carrier. It's the high frequency signal. So FC here is typically, an AM radio that's up in the hundreds of kilohertz range. The 1200 on the AM radio dial is 1200 kilohertz or 1.2 megahertz. On your FM radio, those numbers are actually in megahertz. So 98.6 is in megahertz. Okay. On your over-the-air television, if anyone watches that, they just list channel numbers instead of tuning to particular frequencies. But those frequencies are up in the hundreds of kilohertz, actually above the FM radio band. So there have been a number of different techniques to vary components of the carrier, vary or modulate components of the carrier. Somehow, make it vary in accordance with a low frequency signal, what we often call a low pass or baseband signal. A signal coming directly off of a microphone or a camera that we then impress or modulate on this high frequency carrier. And kind of all the techniques, all the things that you can vary have been varied in some form or another. If we vary the amplitude, we get amplitude modulation. There's still not just one way to do that. There are 4 or 5 different ways to do amplitude modulation. You can vary the frequency of the sine wave. That gets you frequency modulation. Or you can vary the phase to get what's called phase modulation. You certainly are familiar with amplitude modulation and frequency modulation. And television, conventional television did use a form of amplitude modulation, actually, traditional television. The new technique uses a digital waveform and a function of, and actually phase modulation and amplitude modulation. No one's found a way to modulate time yet. That would be time travel if you could change time, I guess. No one's found a way to modulate pi. People have tried to change that, but not been very successful. But pretty much everything else has been tried. But before I get into amplitude modulation, I first want to talk about bandwidth of a signal. So we talk about the bandwidth of a filter, and that can be a little confusing. With a filter, we talk about the frequency response of the filter, and that's the Fourier transform of the impulse response. But we can also talk about the Fourier transform of a signal, and that's something different. And the operation's the same, right? Both cases, we've got a time domain signal, but one is an impulse response. And once the filter is manufactured, that impulse response and frequency response are set. But for the signal coming off of a microphone or out of a video camera, that changes. Okay? It's not always the same. But the Fourier transform of a signal we will often call the spectrum. Now the bandwidth of a filter, typically we talk about the 3 dB bandwidth of a filter. The bandwidth for a signal there are a couple different definitions, and we'll talk about the reasons why. But the definition we're going to use, this is probably the simplest one. It's the maximum frequency in the signal minus the minimum frequency in the signal. Okay. It seems pretty straightforward. There are a couple of cases to consider. So in a low pass, sometimes called a baseband signal, really means unmodulated. But there, F min is equal to 0, and B is equal to F max. Okay. This is actually an example of a baseband signal, a low frequency signal. Actually, it hasn't put time units on here, but this might be a snapshot, a blow up of a signal coming off of a microphone. Okay. It's an analog signal. In that case, the time scale here might be on the order of milliseconds or less. And this would be a corresponding Fourier transform of that signal. Again, it varies, so the Fourier transform will vary in shape, but in this case, the maximum frequency is B, and the bandwidth would be B. When you're talking about bandwidth, it's always just the range of positive frequencies. You know, it's not the total width here, including the negative frequencies. So the bandwidth of this low pass signal would be B. Okay. And you know, some examples of low pass signals are like voice or speech. And it depends on the speaker. Women tend to speak and use higher frequencies than men because of the smaller vocal tract and vocal cords. But typically voice is somewhere in the range from 3 to 5 kilohertz. You know, run into people who have very deep voices. So and when we speak, we actually are creating a range of frequencies. No one speaks with just one frequency. That would just be a pure tone. There's a range of frequencies, but that maximum frequency might change depending on the speaker. Music, on the other hand, we typically, again, it will change depending on maybe the musical instruments that are used to create the music, but typically there we think about bandwidth of music being somewhere in the range of maybe 12 kilohertz up to 20 kilohertz. You know, higher frequencies than just speech. AM radio is only designed to carry really voice. So music has never sounded great on AM radio. AM radio was used for years and years for music, but it's just not capable of carrying the higher frequencies like FM radio. There's nothing inherently wrong with AM. It could be used to carry high quality music. It was just the way it was designed. Now, baseband video signal, on the other hand, so voice, 3 to 5, 6 kilohertz, music, 12 to 18 kilohertz. Video, a wide range there depending on the resolution. But usually, a megahertz up to maybe even 1,000 megahertz for a high definition video signal. The other type of signal, and I'm going to come back to these figures because I want to show what's going on in the figure, but right now I just want to show examples of a low pass signal, and then this would be an example of a band pass signal. And in this case, the bandwidth would actually be 2B. The highest frequency is FC plus B, the lowest frequency is marked as FC minus B, and so that difference here is actually 2B. And then these signals that look like this is what we get when we talk about like a radio signal or a television signal. They're all translated up, that's what we'll talk about, 2 different carrier frequencies. So, the radio station at 1440 kilohertz, there's also a radio station at 1450 kilohertz, whose spectrum wouldn't overlap the spectrum at 1440. So with the AM radio at 1440, its range of frequencies is confined to that 10 kilohertz spacing, 5 kilohertz above, 5 kilohertz below. So, and then with FM, with the 200 kilohertz spacing between channels and FM. So there you've got a 2 kilohertz bandwidth to work with instead of the 10 kilohertz that you're restricted to in AM radio. So AM radio, 10 kilohertz bandwidth, FM radio, 200 kilohertz. Television channels are spaced 6 megahertz apart. They have to do a lot of magic with high def television to make it fit in that 6 megahertz spacing. Because the signal is digital, they actually use a lot of compression technique. They don't transmit the raw digital signal coming off of the camera. They actually compress the digital data. But in television, it's a bandpass signal like this as well with a 6 megahertz bandwidth. Now, some other, I mentioned bandwidth here wasn't necessarily well defined. Because if you look at the Fourier transform, for example, of an exponential signal, it's this hump that never really goes to 0. It's infinite in width. You know, we've looked at this. The Fourier transform is this. The magnitude of the Fourier transform, which is what these plots are, would be the square root of a squared plus omega squared, which looks like this. Okay. So what is the maximum frequency? Well, it doesn't have a clearly defined maximum frequency. Right? And so it's with its signals like that, we run into other definitions like the half power frequency, which is the same as the 3 dB frequency. Or you might hear talk about what band contains 90% of the energy, or 95% of the energy, or 99% of the energy. Those are all different definitions you can hear used with signals. The only form of modulation, amplitude modulation I'm going to talk about today is what's called double sideband modulation. Now this is very close to standard AM radio. It's not quite standard AM radio, and we'll talk about standard AM radio on Wednesday, but it's close to that. So here we modulate by multiplying my low pass signal x of t by cosine. So it's a form of amplitude modulation. Right here I'm replacing the amplitude of my carrier with my low frequency signal. And this is all you need to do to get double sideband modulation. Now, in order to see what that results in a high frequency signal, we have to use the Fourier transform, okay, and talk about the spectrum of Y of M. So Ym of f would be the Fourier transform of x of f, the Fourier transform of our low frequency signal. But we've talked about how convolution in the time domain becomes multiplication in the frequency domain. Well, the Fourier transform and the inverse Fourier transform are very similar integrals. So maybe it's not a surprise. I think we actually talked about it as one of the properties. Multiplication in the time domain, which is what we have here, becomes convolution in the frequency domain. Now, again, we usually try to avoid convolution unless you're convolving with an impulse, right? Because impulses are trivially easy to convolve with. But if you remember the Fourier transform of a cosine, if you look, so this is our convolution symbol. It's been a while since we've seen that. But the Fourier transform of a pure sinusoid consists of two impulses. This would be one at minus FC, and then one at plus FC. And so we can carry out this convolution 1/2 x of f plus fc plus 1/2 x of f minus fc. Remember, when we convolve a signal with an impulse that just translates that signal. Okay, so here is a theoretical low frequency signal. And here is its corresponding Fourier transform. Now, this is the high frequency carrier, and then this is the Fourier transform of the carrier. Now, let me back up just a second. When we multiply this times our high frequency carrier, the easy way to figure out what that's going to look like in the time domain is, I've got my high frequency carrier that's going between plus or minus 1. Okay, it's just a cosine signal. Now the frequency is much higher than the frequency of this baseband signal. But when I multiply this by 1, I just get that. Now I go on the negative half cycle. The next positive half cycle, the peak is not going to go above that value, right? On the negative half cycle, it would just actually be multiplied by that peak value. Okay. And then this continues on. And the easy way to draw what the modulated carrier looks like in the time domain is really just this. The trick is to draw the negative of x of t. I can do that. It's going to cross 0 at the same place. So that's my attempt to draw the negative of x of t. And then the product of the high frequency carrier, my low frequency signal, then it's going to look like that. Okay. This is, again, it's a form of amplitude modulation. You could properly call this amplitude modulation, but most people, when they talk about AM, they mean AM radio, and AM radio uses a slightly different technique. Okay. So this is what that product would look in the time domain. That's the easy way to draw that. And this is what's on the next. Here's the carrier. Here's the Fourier transform of the carrier. And then this is that picture I drew. And he's kind of done the same thing here. This is a figure out of the textbook. So this is the modulated carrier in the time domain, what that would look like on an oscilloscope, right? Now the portion here, the positive portion that connects the positive peaks, is called the envelope of the signal. And we'll talk more about that when we talk about how to receive the AM radio. Right now we're just talking about transmission. This is what the Fourier transform of the modulated carrier looks like. It's just that baseband signal shifted down to negative FC and up to FC, and then there's also this factor of 1/2 that appears. So it's an easy way to think about what happens when you multiply by a cosine in the time domain. What happens in the frequency domain is it just shifts the spectrum to the right and to the left by the frequency of the carrier. Some other terminology that's here. The portion of the spectrum that's above the carrier is called the upper sideband. And the portion of the signal that's below the carrier is the lower sideband. Now, if you remember, we've got this symmetry in any real signal. We'll have this complex conjugate symmetry in the spectrum, but really they contain the same information, right? If I didn't have this part, I could draw it just having the upper part, right? Because I know what that looks like. So there have been some techniques. In some sense, these having both side bands is redundant. So there have been some techniques where I just transmit maybe the upper side band or just transmit the lower side band. Now, at the receiver, I have to recover both side bands. I have to get back my original spectrum. I have to get back my original signal that comes off my microphone so that I can send it onto my speaker. But there have been some techniques that have been developed to do that. The advantage of the single sideband systems is that they have half the bandwidth of the double sideband systems, right? With half the bandwidth, I can stuff twice as many channels into the same spectrum. We've run out of spectrum. There is no more free spectrum. Okay? So that's why we're developing all these special modulation techniques. We had to do away with conventional television because there wasn't available spectrum for HD TV. So we had to just scrap the old spectrum or the old way of doing conventional television. And I expect the same thing will happen with AM and FM spectrum at some point. We'll scrap that, but so standard AM radio is a double sideband technique. It's a little different than what I'm talking about here, but there are also single sideband techniques, lower sideband and or upper sideband. Now, again, this signal can be sent out an antenna. You know, FC here is usually on the order of hundreds of megahertz or megahertz or above. And then we might have multiple channels either going out wirelessly from, you know, the same area that your receive antenna is pulling in all of these different signals, or they might be on a coaxial cable and then using different carriers so that they don't overlap. Now, we have to recover the original spectrum. At the receiver, we demodulate using we multiply the modulated carrier, what do I call it, Y of M, by a cosine of the same frequency. Where's on there? Multiply by a cosine again. Now, in practice with AM radio, this is not how AM radio is received. There's a much easier way to do this with AM radio, involving just a diode and really just a half-wave rectifier, what's called an envelope detector, but we'll talk about that next time. This will work. This will work to receive standard AM radio. Okay, so taking my formula for Y of M over there, which was just X of T cosine, and carrying this out, I'll get X of T times cosine squared from the math. And I should mention too that at my receiver, I'm not going to get a perfect replica of Y of M. It's probably going to, maybe some distortion. There's certainly going to be noise added. It's not going to be exactly the same signal that was transmitted from the transmit antenna. But assuming we've got no noise, using a trig identity, cosine squared of, well, cosine A times cosine B is 1/2 cosine of the difference plus 1/2 cosine of the sum. Okay, here I've got cosine A squared, so I have 1/2 cosine of the difference, so I have cosine of 0 or 1 plus 1/2 cosine of the sum, and instead of writing this, so 2 pi FCT plus 2 pi FCT would give me 4 pi FCT, but instead of writing it like that, I'm going to write it as 2 pi FC of t so that it's obvious that that term is a sinusoid at 2FC now. And then the next step is low pass filtering. Now here, when I multiply this through, I'll have 1/2 x of t, 1/2 x of t cosine times 2fc. So x of t cosine of 2fc, that's another AM modulated signal, but now up at twice the carrier frequency. So, you know, if originally I was modulating using a carrier frequency of 1 megahertz, this would be up at 2 megahertz and centered around 2 megahertz, plus or minus, 5 kilohertz or something. So low pass filtering is going to completely eliminate that. Okay, I think I've got more pictures here. So y out of t would be low pass filtered version of yd of t, but that's just going to be then 1/2 x of t. Okay. That's in the time domain. This figure is actually showing what happens in the frequency domain. So let's look at that. In the frequency domain, yd of f would be my modulated carrier convolved with, and this is just multiplication, so ym of f convolved with 1/2 delta f plus fc plus 1/2 delta f minus fc. But ym of f, I've got it over here, is 1/2 xf plus fc plus 1/2 xf minus fc. So if I take the 1/2, well, let me convolve the 1/2 xf plus fc through. I'll get xf f plus 2fc plus 1/2 xf plus fc but minus fc. And then now when I take the 1/2 xf minus xf minus fc through, I'll get 1/2 xf of f plus 1/2 xf minus 2fc. Those two terms are the same. Actually, I screwed up here, didn't I? When I take my 1/2 times my 1/2, all these would be 1/4. And I add these together, I'll get 1/2 x of f plus 1/4 x of f plus 2fc plus 1/4 xf minus 2fc. And so what is this? What am I left with now? This is my original signal times 1/2. This is my original spectrum, slid down to minus 2fc. This is the original spectrum slid to the right by 2fc. And that's what this picture is showing. So, here's my double sideband modulator, just multiplied by a cosine. Here's my demodulator, I just multiply by a cosine again. And then that gives me this spectrum. I would have, another way to look at it is, this spectrum I'm going to modulate using by FC. So I'll take it, slide it to the left by FC, take it, slide it to the right by FC, and add all those components together. So I get twice the component here at 0. That's what I did there when I added those together. So you end up with, let's hit freeze. So we end up with, our original spectrum. Again, don't worry about the 1/2. That's what your volume controls on your radio for, right? So that you can adjust. These are just multiplying all frequencies by a constant. So you can adjust. They're really irrelevant. You can adjust the volume to a comfortable listening level. So, but it's 1/2 times my original spectra. And then I've got replicas of my original spectra up at 2 times the carrier and -2 times the carrier. So I can easily filter those out with a low pass filter. And typically this is maybe on the order of 5 kilohertz. This is hundreds of megahertz. So this is not the scale at all, right? This replica would be way out there. Low pass filtering is just going to recover this spectra, which is exactly what I want. So that's kind of how AM radio works. There's some things I've glossed over. It's pretty important that we have exactly the same cosine signal at the receiver that we have at the transmitter. It has to be exactly matched in frequency. And you might think that's pretty easy, but it's not, because they're separate oscillators. And so even though we've got these function generators here that you can set to a particular frequency, if you have independent oscillators, they're probably going to be off a few hertz or hundreds of hertz, depending on the oscillator that's used. They also have to be synchronized in phase. They have to have the same phase. If they're 90 degrees out of phase, you can show that if this is a cosine and this is a sine, you actually get nothing out, okay? Because a cosine times a sine actually gives you a 0 at baseband. So they have to have the same frequency, they have to have the same phase. That's not easy to do. So again, standard AM radio actually does something a little different. They don't do this multiplication by a cosine. They use what's called an envelope detector. The other thing that I've glossed over is this multiplier. Okay, you guys have seen circuits that add voltages together. It's pretty easy to do that. Okay. But I doubt that you've ever seen in your electronics classes an analog multiplier, right? These are analog signals that we're working with here, and we need to multiply them. It's easy to do when they're digital signals on hardware, a digital multiplier, but an analog multiplier is a different animal. I'll talk about that just briefly. It's kind of 2 standard ways to do that. Analog multiplier. One technique, actually, this seems crazy, but we can show that the product of 2 signals is equal to the square of the sum of the 2 signals minus the square of the difference. Okay, you get an x squared here, that cancels here, and a y squared term, and you're left with you'll get a 2xy here minus a negative 2xy. So that would be 4xy, and then did I do that right? You'll get out 2xy minus a negative 2xy. I guess this actually gives you 2xy, doesn't it? Okay. But you got something, could multiply by a quarter. My math may be off. Is that right? That would give me a 2xy minus a negative 2xy of 4xy divided by 4. So yeah, I think that's right. It seems like a crazy way to do multiplication, except for the fact I mentioned we've got ways to add signals together analog signals together. We've also got devices that can actually compute the square of an input signal. Have you run into any in electronics? Any devices where maybe the output voltage is the square of the input voltage? Related to the square of the input voltage? Haven't run in, I thought a MOSFET had that square law transfer function between the gate voltage and the collector voltage, doesn't it? Don't you remember that? No? A MOSFET will do it, actually. And then you can actually use almost any nonlinear device, actually. So you can actually use a diode as a square law device, even though it's got this exponential relationship. If you expand it in a power series, it's got squared terms and higher order terms that you may be able to filter out. But I think that's what, so this is a block diagram of that technique of, yeah, it is a one quarter, of actually generating the product of two signals, an analog multiplier. Here for these square law devices, again, typically MOSFETs or diodes. Alternatively, another technique a switching modulator can be used to form Ym of t is x of t cosine of 2 pi fc of t. Okay. Now, a switching modulator is not a general analog multiplier, but it will multiply, it can be used to generate the product of x of t and a sinusoid, which is what we need. And then the technique is actually pretty simple, at least in block diagram form. That we have x of t that we sample. So I close the switch and open the switch at a very high rate. So this, instead of a switch, it would probably be some sort of solid state device, some sort of transistor switch. And then bandpass filter at FC to get the modulated signal. And now the way this works is that I can actually model, I call this W of t is on this side of the switch. I can model W of t as just x of t times P of t, where P of t is just a pulse train. And like that with a period of TC. Because I'm just closing the switch, letting a portion of x of t pass. And so if P of t looks like this product is going to be equal to x of t during this time interval, 0 here, and then whatever x of t is in that interval, okay, and so on and so forth. So a way to model what that switch is doing is the product of P of t times x of t here, mathematically. But P of t is a periodic waveform. And so it has a Fourier series representation. K equal 1 to infinity plus Cn cosine. And it would be multiples of the fundamental, with some amplitude and phase angle. But I'm switching at this rate that's equal to my desired carrier frequency. So if I want to modulate at 1 megahertz or whatever. So I can write W of t mathematically as x of t times this, C0 x of t, which is really, that's just a scaled version of my baseband signal. That's not really what I'm after. And then I get this term C of n x of t cosine of 2 pi fc, I left off my t, fc of t plus theta 1. And then all these other terms, k equal 2 to infinity of Cn x of t cosine of 2 pi n fc of t plus theta n. I pulled that one out because my bandpass filter, I have a picture of that. I guess I didn't. Oh, I drew it. My bandpass filter is just going to pass. So this is modulation again, right? Here I've got my baseband signal. The product here is equal to the sum of my baseband signal plus my signal modulated up to FC, plus it modulated to 2FC, 3FC, 4F. But FC is so large, you know, these components are far apart in the frequency domain. Right? Multiplying by a cosine translates to spectrum. That's the basis of all of modern wireless communications. So my bandpass filter is just going to pass the component at Fc of t, which is my modulated, my double sideband modulated signal. Got that phase constant in it and multiplied by the amplitude, but that's not important. Which is what so an easy way, at least on this block diagram, to generate a double sideband signal. Just my signal coming off my microphone, high frequency switch here, and then run that through a bandpass filter would give me my double sideband signal. So we'll talk more about this on Wednesday. We'll tell you what AM really is and how AM is really demodulated. We're not going to get into FM. Those of you who are in electrical engineering get a whole course on that next year. Yeah, I know you're looking forward to that.